Good. So today's example is quite an interesting example. So the idea is that when people are being told that they're drinking wine from a more expensive bottle, they will consider this to be the better wine. That is kind of an interesting example because I think it holds true in many cases that the price determines how people think about the wine. So in population one, people are told that they're drinking wine from a $10 bottle. In population two, they're told they're drinking wine from a $90 bottle. The distribution here is the distribution of the differences between means rather than the distribution of mean difference scores. That's the difference. So the distribution of mean difference scores, that would be the paired sample t-test. Now we have a distribution of differences between means in little subsamples that we have randomly drawn from our two samples of wine drinkers. Assumptions are just with the paired sample t-test. They were not randomly selected, which is mostly the case with convenient samples. So you always need to be careful with generalizability. So if it's not randomly sampled and convenient sample, always think of this not being generalizable. We don't know whether the population is normally distributed, and these are indeed the right tests to use. So hypothetically, that would be a roadblock to actually using a parametric test, but for the sake of examples, we can go ahead with that. And this is just an overview of this comparison distribution. And I'm flagging this, make a note of this table, because that's essentially how you determine these comparison distributions. If you have a set test where you only have one sample, you're comparing that one sample against your population mean. You get a distribution of means of that one sample. Same concept with the single sample data. You have one sample and you only compare the distribution of means against your population mean, and you use that to standardize the difference between a sample mean and your population mean. Make sure that you know how to distinguish between those two, because the set test, what is the difference? The difference is you have the standard deviation of the population. That makes the difference. With the single sample t-test, you're estimating the standard deviation based on the standard deviation in your sample. With some arithmetic modification, we're dividing now the variance by the degrees of freedom rather than the sample size, as we did in the population. The paired sample t-test, we choose samples again, but we have the same participants from before to after. And the comparison distribution is the distribution of mean difference scores. Independent sample t-test with two samples again with different participants, and the distribution of differences between those means of hypothetically repeated samples will basically allow for us to calculate or to standardize the difference between the two sample means. Okay. Any questions to that? I think it's quite intuitive. It's the mean difference scores to differences of means. That's maybe a little tricky, but I think overall it's a rather simple concept. What is a little bit more involved is how you actually calculating that, and that makes it a little tricky. So and today is a little bit more involved. So we have now, first, we need to step one. So we made our assumptions. We have our two populations. We know that we have an N of 4 in group 1. So N1 is 4, whereas N2 is 5. We're calculating now, first, our average. So the average is calculated. This is average. So we're calculating now 2.5 versus 3.7. That's our average. So we see already that the rating of the very same wine was substantially higher in those that were told that this is a more expensive wine. So now average is already different. The question that is being asked now next is this actually true now also statistically? And this is the calculation we're going to do next. So now we have 5 stages that need to be done. So now we see 2 differences between the 2 groups. So if we're calculating now the standard deviation of these 4 entries, this will give us standard deviation of 0.80 for sample 1 and the standard deviation of 0.99 for the second group. So what's the problem with this? So if you were to calculate it, let's assume these were 2 independent groups and we would compare this to a reference value, a random reference value or population mean. Our standard error of the mean would already would be substantially different for these 2 samples. And that is also the problem, because you need to account for that. Because if you're calculating now the differences between sample means and you're using that as a comparative distribution, your standard error of the mean that you use to standardize your actual difference needs to account for the variance of both samples. Because each of these subsamples that you're drawing to create those pairs and calculate that individual difference that then in the end leads you to this distribution of differences between means is going to be affecting the accuracy and the variability of each individual mean estimate. And consequently, the variability of this comparison distribution. Therefore, we need to first calculate the variance for each sample. We need to pool the variances. We need to convert the pool variance from a squared standard deviation by dividing the pool variance by the sample size. That sounds a little bit more involved, but basically what you do, you get an estimate of the variance for each of your samples. You pool this together with a weight for the sample size in each of your samples. And this pooled variance is then used to calculate your actual standard deviation that serves to standardize your difference. Let's go through that. Let's go through that step by step. So firstly, we calculate our standard deviation. So we have done that with 0.8 and 0.99. But we want to come back to the variance. So we want to actually square this again and calculate the variances. You can also do this. There's actually another way how to do that. You can do VAR, variance S. Oops. Variance S is actually the Excel function to do that. And you can, with variance S, you basically can calculate the variance directly. You don't need to calculate first the standard deviation. You can just calculate it directly. But you basically have now 2 variances. So if we are going, moving this a little out there. So now we need to pool these variances. And we know now that we have a sample size N1, N1 and N2. So this is 4 and this is 5. Then we also have degrees of freedom 1 and degrees of freedom 2. So that is 4 minus 1, right? So we have degrees of freedom of 3 and 4. And now we're pulling this together and we're saying, okay, so this is degrees of freedom total. And that is now the sum of 3 and 4, 7. So there's a reason why I'm doing this that complicated, because there's some logic to that. So you basically have 7, 3, and 4. Each of these contributing degrees of freedom have a weight. They have a proportion in the estimation of the total degrees of freedom. And this proportion, you basically can calculate as 3 divided by 7. Or 4 divided by 7 for sample 2. And this obviously needs to add up to 1, right? Logically. So now why am I doing this? Because what is being done was with this pooled variance. So you get the variance calculated as the individual deviation squared divided by the n minus 1. That gives you the variance. You then move on to take this variance and you multiply it with that proportion until it adds up to 1. So you're assigning weight in the estimate of the overall variance. So this is the overall variance. And you assume that the variance pooled should be the sum of each individual variances, right? So hypothetically, it's 2 variances would give the overall variance for 2 samples. But you're distributing weights to each of these variances according to the sample size within that sample. So the way this looks like, you have now a pooled variance if both samples would be the same size, could hypothetically be variance and variance. So where you say, okay, so this is this and this. So it could be the sum of these two, if they were the same size. So this would be a sample where you have equal variance. But this is not what we have. We have 2 unequal variances and we have 2 unequal sample sizes. Therefore, we need to calculate it with this pooled variance equation. I'm going to copy this over. And this is very easily calculated. So we have that proportion, this decrease of freedom of x divided by the degrees of freedom of total is nothing else but this calculation. This is the proportion. This degrees of freedom of y divided by degrees of freedom total, nothing else but this proportion. So all you need to do is to basically calculate, let's get this done. You calculate your variance of x multiplied by that proportion. You calculate the variance of y with that proportion. And you calculate the pooled variance as the sum of these two. But they are weighted. And that is really the key to understand the pooled variance. It's a weight of the respective sample size in each sample. Okay. But it's considerably simple. It's like once you have kind of followed along, it's considerably simple concept. Good. Once we have this pooled variance, we need to now calculate our standard error of the mean. And again, there we need to account for 2 samples, because each of these samples again come together. So that's why we need 2 different standard errors of the mean. And these standard error of the means need to be accounted twice and first calculated. So our SM is now essentially our SM is basically this multiplied by this proportion. For a second. So we need to take, now that would not be the same. Now we need to do this. Okay, so we have now a pooled variance. So we need an SMX and an SMY. And so now this will take the pooled variance divided by our sample size, because it would be standard deviation divided by square root of the n, the square root of the n. So, but now we're looking at the variance, so we need to square everything. So it's now variance divided by the n, no square root. So we're basically doing pooled variance divided by our n, which is 4 for x, and it is 5 for y. Adding this up would give us now this, what it's called, that's the standard error of the differences between the means. So our SEM is here the sum of these two. And there it becomes a little bit more involved, right? So you have an S, so this is the squared standard error, and now the square root will get you to this actual standard error. And this is the first time you're actually employing. So this is SEM squared. Now the SEM is basically this square rooted. This gives you a standard error of the mean of 0.61 or 62. So now the rest is simple, right? Well, not really that simple, because there's another caveat. So this is the formula that is being used for the calculation of your t. So just as you would expect, you have your actual difference that you're testing against. So under the null hypothesis, we know so HR is that the M1 minus M2 equals 0. Whereas HA is M1 minus M2 is different than 0. Right? That's your null hypothesis. That's why you need to calculate, when calculating your t, you need to subtract my from mx against your null hypothesized difference. The same as with the paired sample t-test, where we subtracted 0 from our difference or mean difference. Now we're subtracting whatever we are null hypothesizing from our difference. So it's the same principle. So if you expect the difference for whatever reason, because M2 was in the 80s, it was a group of octogenarians against a group of, I don't know, high school students, you expect the difference. If your null hypothesis is already comprising that there will be an expected difference, you need to add this expected difference in your null hypothesis. But in the simplest way of hypothesis testing, you would assume a difference of 0 under the null hypothesis. So this simplifies then to exactly that in the simplest form. But it's important because there may be an expected value, an expected difference, and you would need to account for that. So if you have now mx minus my, that would be mx minus my divided by the standard error of the mean. So that gives you a t of minus 1.948. For the sake of making this a little bit easier, let's do n minus m, because automatically it comes to the same thing. So the t is here 1.95. If we want to calculate the critical t, we need to read that from the t-square distribution table. We know our degrees of freedom total was 7. So we know the critical t we're testing against is 2.36. So our critical t is 2.36. So we see already that there's no significant difference between both. And it's 2.44. For the PK for a second. 0.61. Interesting. Oh, wow. Okay, my apologies. Make sure, please, if you extend the average to include the last number. So you just copy the formula over, and this is why it's so important to always double check your calculations. You always need to extend it all the way to the last. So what happened is, like, I dragged it to the second column, and it wouldn't extend to the last number. So this needs to be N10. So now all the way down there, so we have now a t of 2.44. Or we can actually call this also. So now we're basically rejecting our null hypothesis and accepting now the research hypothesis. So what is the conclusion of this? We basically know now that a wine will be rated better if it's labeled as a more expensive wine. Good. What can we do next? We can calculate now our 95% confidence interval. What we could also do, we can calculate now with t-test. Oh yeah, let's do that first. So we can basically calculate now our t-test also with the internal function. So remember from last time when we did the paired sample t-test, if you open t-test, you basically get here with the formula builder that you open on the left top, you get here 4 different menus and 4 different entry fields. So with array 1, you're basically marking the first 4 entries of the $10 bottle group. With array 2, the $90 bottle group. Tails is 2-tailed. And type is now, so we have paired equals 1, would give you a paired sample t-test. 2 sample equal variance, homoscedastic would be 2. And 2 samples unequal variance would be 3. So as we have determined, our variance is unequal. So we're basically entering 3 here. And this result here essentially is the p-value. So we know now that the p-value, and that's our type 1 error, right, for our comparison is 4.1%. So that's how we would calculate this in a t-test example. So we know that the 2.44 is exceeding our 2.37, 2.36. And yeah, so we can now embrace the research hypothesis and reject the null hypothesis. What Nolan and Heinzen also want to emphasize here, so as per the APA standard, you are reporting statistics. And this comes back to the independent sample test. That's a very common test. So it's important that you know how to report it. You would report t-score for all your analysis in this format, where this you state t, or degree of freedom of 7, was followed by the actual t-score, followed by a conclusion to of the p-value. So if you would report this, this would be a t of 7, translates into 2.44 with a p, smaller p or larger p smaller than 0.05. In our case, because we calculated that p, we could also say p equals 0.04. That's another way how we do that. So if you know an exact p, you would report this p. Okay. Any questions on this? I know this is a little involved, but keep in mind how it was calculated. So essentially, all you do, you calculate your averages, you calculate your variances for each of these two samples. You come via the degrees of freedom, where you calculate the proportion of the respective degrees of freedom in your sampling, based on the overall degrees of freedom, which is the sum of the degrees of freedom for those samples. You multiply your respective variance in the group with your weight. You're adding this to get an actual pool variance. You're squaring this to essentially, or you first get the pool variance. From the pool variance, you get an actual standard error of the mean for each of these distribution. You're pooling the standard error of the mean, and you utilize this standard error of the mean to calculate your t based on this equation here on the right. You determine your critical t, and you get then to your actual p-value estimate, and whether it's smaller than 5% or not. And this is the way you would report it. So now we get to the confidence intervals. And also here, essentially, you would do it in the same way. So you basically, you would calculate the difference between average 1 and average 2. So M1 minus M2. This is N12 minus M12. So that's 1.5. You calculate now your lower limit and your upper limit. And your lower limit is basically your difference minus your critical t multiplied by your S difference. And in the same fashion, you calculate your upper limit, you calculate your difference, your mean difference, you add your critical t multiplied by the standard error of the mean. And what you see here again is just in the same fashion. You basically you can conduct your null hypothesis, your hypothesis test already with the 95% confidence interval, where basically you would pay attention that the upper and the lower limit does not contain the value that you've seen under your null hypothesis. So that would be 0. So 0 is not contained in this difference. So you're basically testing it against your null hypothesis of 0. If this is not contained in your 95% confidence interval, you would reject the null hypothesis as this being significantly different. Good. Any questions? So this is basically a graphic depiction of the 95% confidence interval. So that's our estimate. So just don't get distracted by minus 1.5. So you can subtract one versus the other. Arithmetically does make a difference because remember the normal distribution is symmetric. We can, of course, also calculate an effect size. And that is in the same fashion done. So we have here 95% confidence interval. Now we're calculating the effect size. So for that, we need a pooled standard deviation. And the pooled standard deviation essentially is nothing else but the square rooted pooled variance. And then we're calculating our mean difference minus 0 divided by our pooled standard deviation. So 1.63 is the effect size that we observe in our comparison. As we know, this effect size is, as per Cohen's definition, a large effect size. Make sure that you study and understand the actual intervals. The small to medium is 0.2 to 0.5, medium is 0.5 to 0.8, large is greater than 0.3. Also understand the corresponding overlap and what that actually means. So keep in mind, the less the overlap, the more likely the effect is strong. So the stronger the effect, the smaller the overlap. There's an inverse association between those two. Yeah. A Bayesian approach to data analysis. I'm not going to go anywhere in detail into this because it just becomes a much more complicated conversation, a much more conceptual conversation. Basically, Bayesian approaches represent a shift in statistical thinking. It includes a prior belief. And I intuitively, when I talked about expected differences, that's already including a prior belief. So when I talk about exercise minutes between two samples, and I'm comparing the exercise minutes per week in two different samples, and I say I have a group of octogenarians and I have a group of high school students, it's more likely the high school students are going to be more active. That may actually depend. Could be true, could not be true. So this is a prior belief and a prior established probability. And this basically can, in many cases, be used to draw conclusions that are more informed than just doing hypothesis testing. Same principle in a way applies than when you had the comparison between what was it, mathematical performance in men and women, and comparing the difference between biological sex. And you need to take into account the whole distribution, the whole bell distribution. That's why it's important to use new statistics and the 95% confidence intervals to understand the entire spread of the distribution. Same concept applies here in some shape or form. It's just you cannot solely rely on hypothesis testing and making an inside binary and to say, yes, that's how it is. You need to take into account prior beliefs and prior information. Where Bayesian statistics become particularly important, and you have heard that, is in the context of diagnostic testing. if you do diagnostic testing in somebody who has already symptoms, you're more likely to have a positive result. And believe it or not, diagnostic tests are actually terrible. They're actually not very accurate. For example, you know in principle what a myocardial infarction is, right?
Or it's a heart attack.
Exactly. A heart attack, most commonly you would diagnose this, you would think, was an electrocardiogram, which is measuring the electrical activity of the heart, which can be reflective of a heart attack. The diagnostic accuracy of an EKG, brace yourself for some interesting piece of information, the diagnostic accuracy of electrocardiogram is kind of the gold standard out there in the field, is 65% accuracy, diagnostic accuracy. So that's like a notch better than flipping a coin.
You could see abnormal heart rhythms on it though. Like they're
Yes. No. I'm just saying, like, as a diagnostic tool to diagnose heart attack. Of course, it's not. I'm simplifying things. Don't make me.
Sorry, I put on a lot of EKGs in my life. I put on a lot of EKGs in my life. Like
Yeah.
it's arrhythmias.
Join the club. But yeah, so it is for the diagnosis of heart attack not really a good suitable tool. But what you have symptoms, and symptoms create a prior belief, and symptoms create for you what is labeled in diagnostic statistics a pretest probability. And this pretest probability does then essentially inform your post-test probability. So there is actually 65% is actually not too bad. So this is what it comes down to. So you need to kind of keep pretest probabilities in your mind when you do hypothesis testing. So that's my short spiel about Bayesian statistics. I'm not going to go too deep into it. A little historic fact. That's actually a fun fact. Bayesian statistics were invented by Reverend Thomas Bayes in the 18th century. And he was a clergyman and a statistician in the UK, Great Britain. And what he did, he basically came up with this concept, and he said, like, okay, so you have a probability. If you roll a die, you basically have a probability of 1/6. So now you have a mutually exclusive event if you roll it twice. So it's 1/6, and then second time it's again 1/6. What if you think of a scenario where you do something repeatedly, but each time you do it, it informs the probability on the second time? So diagnostic testing, pretest, you do the actual test, you put the EKG on, you measure, and you use it for diagnostic and post-test probability. So what he did, he actually took a huge pool table, and he would stand in front of the pool table and roll without looking a ball, trying to identify a specific point where the first where another ball, an independent ball, was lying. And he would get from a second independent observer only information how close that ball he rolled was to the initial first ball. And by that, he was able to inform the probability to then essentially hit that ball, which location he did not know. That sounds now, it sounds a little complicated, but so if you do that 100 times, you get assessments and you get kind of probabilities of hitting that ball. And well, clergymen in the 18th century maybe had time to do that. So they would do these assessments that way and would basically get data sets that allowed them to validate their mathematical theories, how to quantify that. So that's just a little bit of an historic background, how Bayesian analysis Bayesian statistics were invented, so to say. That's called Bayes theorem. Good. Any questions about anything of this? Make sure, please, to understand the terms that we have used today. Understand the effect size, the overlap. I can't emphasize that enough. Know what the pooled variance is. Know how you aliquot I call it aliquot, but you basically you attribute weights to each respective variance. By doing that, you basically get a pooled variance incorporating these weights and the variance of each respective sample. You get down to an actual standard error of the mean, which comprises information of both samples, and that allows you to actually hypothesis testing. Keep in mind that the null hypothesis is here that whatever this expected difference is, needs to be subtracted from the actual difference. That is important. That is really, keep this in mind in case you're facing an example like that. Remember the t-test function. Remember that this can be used to quantify a p-value. And, well, know how to report. That's always important. You may see that short essay question, may be helpful to know. Good. Besides that, I'm pretty much finished. If any questions concerning the midterms? Yes. Excuse me?
Where does the material stop for the midterm?
Chapter 8. So this is not on the midterm. This is not on the midterm.
Yeah.
Go. So we have chapter 1 to 8, and since this is a spring, we don't have that additional class that we could have used for a review session. But I think you have the lecture recordings at your disposition, and make sure to rewatch those, particularly those that are particularly relevant for the midterm. I would suggest to basically rewatch hypothesis testing and confidence intervals. At least go through the spreadsheets, know how to calculate things, know how to use the functions in Excel, the median functions, average functions. These are simple. You will not be asked to do an Excel example like that, but there may be calculations where it may be helpful that you use Excel rather than do it with a calculator. That's really up to you. Yes, please.
Does it test whole class, like an hour and 15 minutes, or?
It should be, no, it's a total of 25 questions. Yeah. If no further questions, have a nice evening. Thank you.
So, I one day, I was